Our planet is constantly bombarded by invisible travelers from space. Most are blocked or scattered. But one, the neutrino, is different. Nicknamed the ghost particle, it can pass through an entire planet as if it were empty space. For decades, we've built colossal detectors buried in Antarctic ice and deep in the Mediterranean Sea to catch these fleeting messengers. We're listening for whispers from the universe's most violent events. But recently, we didn't hear a whisper. We heard a scream. A single, ghostly particle of such ferocious energy that its origin defies our current understanding, igniting one of the most exciting investigations in modern astrophysics. The quest to see the universe in neutrinos is a study in patience. At the South Pole, the IceCube Neutrino Observatory uses a cubic kilometer of ice filled with over 5,000 light sensors. They wait for a high-energy neutrino to strike an atom, creating a faint flash of blue light. From this flash, scientists can figure out the neutrino's energy and where it came from, turning the ice itself into a cosmic telescope. For years, IceCube has been mapping the high-energy sky, even tracing one neutrino back to a flaring galaxy core called a blazar in 2018. But some detections are deeply puzzling. On September 22, 2021, IceCube detected an event with an immense energy of 750 trillion electron volts. Yet, when astronomers pointed their telescopes to its origin point, they found nothing. No exploding star, no flaring blazar. It was an orphan neutrino, a message with no return address. Then, in February 2023, the mystery deepened. The KM3NeT detector, still being built off the coast of Sicily, captured a neutrino of truly staggering power, estimated at over 100 peta-electron volts. That's 100,000 trillion electron volts. This single particle carried more than 10 million times the energy of anything we can create at the Large Hadron Collider. And just like the IceCube event, its origin was a complete blank. What in the cosmos could launch a ghost particle with such force? In a groundbreaking paper, physicists at MIT proposed a prime suspect, and it's an object straight out of the dawn of time, an evaporating primordial black hole. Primordial black holes, or PBHs, are purely hypothetical. Unlike the black holes we know, which form from collapsing stars, PBHs are thought to have formed in the ultra-dense chaos of the first second after the Big Bang. Tiny fluctuations in density could have become so extreme that some regions collapsed directly into black holes. This means they could exist in a huge range of masses, including the asteroid mass range, from about 10 to the 17th to 10 to the 22nd grams. Crucially, in this mass range, PBHs are a leading candidate for dark matter. The theory suggests the vast, invisible halos of dark matter surrounding galaxies, including our own, could just be a swarm of these ancient asteroid mass black holes. So how does this connect to our impossibly energetic neutrino? In 1974, Stephen Hawking predicted that black holes aren't truly black. Due to quantum effects, they should slowly leak a faint glow of particles, now called Hawking radiation. For a big black hole, this is undetectably slow, but for a small black hole, the process is much faster. A smaller black hole is hotter and radiates more energetically. This creates a runaway effect. As it radiates, it loses mass, gets smaller and hotter, and radiates even faster. For a PBH with a mass below a certain threshold, this process would have caused it to completely evaporate by now. The final moments of this evaporation are cataclysmic. As the black hole shrinks to the size of an atom, its temperature skyrockets into the trillions of degrees. In its final nanosecond, it unleashes an explosive burst of all fundamental particles, including a torrent of neutrinos. The MIT researchers calculated that this final explosion would release neutrinos with energies clustering right around the 100 PeV scale, a perfect match for the record-breaking KM3NeT event. The implication is breathtaking. If the dark matter in our galaxy is made of PBHs, then statistically, a small number of them should be reaching the end of their lives and exploding right now. The ghost particle wasn't from a distant galaxy. It may have been the dying breath of a microscopic black hole in our own cosmic backyard. This single hypothesis elegantly ties together three of physics' biggest puzzles: the origin of ultra-high-energy neutrinos, the existence of primordial black holes, and the nature of dark matter. But a good story needs testable evidence. The strongest clue in favor of the PBH hypothesis is the very thing that makes the detection so mysterious: the lack of a visible source. A conventional source, like a blazar, is a messy, violent place. If it makes a high-energy neutrino, it should also produce a blast of gamma rays and other light. An evaporating PBH, however, is a clean explosion in the vacuum of space. It produces vastly more neutrinos than gamma rays, and those gamma rays can be blocked by interstellar dust, while the neutrino travels straight to us. This creates a unique orphan neutrino signature, which is exactly what we've seen. The theory also makes a testable prediction. If PBHs make up our galaxy's dark matter halo, these explosions should NT be random. The dark matter halo is densest toward the center of the Milky Way. Therefore, we should expect to see more of these ultra-high-energy neutrinos coming from the direction of the galactic center. With only a handful of events so far, we can't confirm this pattern yet, but as more data comes in, a clustering of events towards the galactic core would be monumental evidence. There's one theoretical wrinkle. Standard Hawking radiation predicts that any PBH exploding today would have had a specific initial mass. However, some newer theories suggest that as a black hole shrinks, the information of what fell into it resists being destroyed, a phenomenon called the memory burden effect. This would slow down the final stages of evaporation, extending the black hole's lifetime. It means that even lighter PBHs could have survived to the present day, making it more plausible that we are witnessing these explosions now. Of course, the case is far from closed. Skeptics point out that an explosion close enough to send us such an energetic neutrino should have produced some detectable gamma ray signature, even a faint one, which wasn't observed. And we can't rule out other, as yet unknown cosmic phenomena. The universe is always more inventive than our theories. The beauty of this idea is that it is testable. The coming years will be critical. The IceCube Observatory is getting a major upgrade, IceCube Gen 2, which will expand its volume tenfold. This, along with the full operation of KM3NeT and other planned detectors, will dramatically increase the rate of neutrino detections. More data means better statistics to check for that directional preference towards the galactic center. Furthermore, coordination between neutrino observatories and traditional telescopes is faster than ever. If another orphan PeV neutrino is detected, a rapid, deep search for any faint counterpart, like a flicker of gamma rays, will be crucial. Finding a correlated signal would be the smoking gun. We may be on the verge of a revolution. Confirming that a primordial black hole was the source of this cosmic messenger would not only prove Hawking's theory of evaporation, it would likely mean we've finally found dark matter. The invisible stuff holding our galaxy together would be revealed as a vast swarm of microscopic black holes, fellow travelers, since the beginning of time. For now, the investigation continues. The giant, silent eyes of our neutrino telescopes remain open, staring into the cosmic dark, waiting for the next ghost particle to arrive. They are listening for another scream from the void, hoping it carries the answer to one of science's greatest mysteries.